It's kind of crazy that the quantum computer have been revolutionized by principles of the so-called quantum technology. Quantum computers are a revolutionary new type of computer that harness the principles of quantum mechanics to perform computations in a fundamentally different way than classical computers. While classical computers store information in binary bits that can be either 0 or 1, quantum computers use quantum bits or qubits that can exist in a quantum superposition of 0 and 1 states simultaneously. This quantum superposition is a core concept in quantum mechanics that allows qubits to encode more information than classical bits. Instead of being restricted to just 0 or 1, a qubit can be in a linear combination or superposition of both 0 and 1, with associated probabilities for measuring either state. This superposition allows quantum computers to explore many possible solutions to a problem in parallel. Another key quantum mechanical property that enables the power of quantum computers is quantum entanglement. Entanglement describes a special quantum mechanical correlation between multiple qubits, where the state of one qubit depends on the state of another, even if the qubits are physically separated. This allows quantum computers to perform certain computations exponentially faster than classical computers. The fundamental unit of information in a quantum computer is the qubit, which can be physically realized in a variety of ways, such as using the spin of an electron, the polarization of a photon, or the state of a superconducting circuit. Unlike classical bits, qubits are extremely fragile and susceptible to errors from environmental interactions, a phenomenon known as decoherence. A major challenge in building practical quantum computers is overcoming decoherence through the use of quantum error correction techniques. This involves encoding each logical qubit into a larger number of physical qubits, allowing the quantum computer to detect and correct errors. However, implementing effective error correction at scale remains an active area of research. Despite these challenges, significant progress has been made in recent years in developing small-scale quantum computers with tens of qubits. These devices have demonstrated the ability to perform certain specialized computations faster than classical supercomputers, a milestone known as quantum supremacy. However, building a large-scale, fault-tolerant quantum computer capable of outperforming classical computers on a wide range of practical problems remains an immense technological challenge. One of the most promising applications of quantum computers is in the field of cryptography. Quantum computers have the potential to break many of the encryption algorithms that currently secure online transactions, communications, and sensitive data. This has led to a race between cryptographers and quantum computer researchers to develop new encryption schemes that are resistant to quantum attacks. Another key application area for quantum computers is in the simulation of quantum mechanical systems, such as molecules and materials. Classical computers struggle to accurately model the complex behavior of quantum systems, as the computational resources required grow exponentially with the size of the system. Quantum computers, on the other hand, are well suited to simulating quantum phenomena, as they can directly leverage the underlying quantum mechanical principles. Quantum computers could also have significant implications for fields like optimization, machine learning, and the search for new drugs and materials. Many of these problems involve searching through an exponentially large space of possible solutions. A task that quantum computers may be able to perform much more efficiently than classical computers. The development of quantum computers has been driven by a global race, with major investments and research efforts from governments, tech companies, and academic institutions around the world. Countries and companies are vying to be the first to develop a practical, large-scale quantum computer that can outperform classical computers on a wide range of important problems. While the potential of quantum computers is immense, the path to realizing this potential is fraught with significant technical challenges. Researchers must overcome obstacles related to qubit control, error correction, and scalability to build quantum computers that can reliably outperform classical computers on real-world problems. Despite these challenges, the field of quantum computing has seen rapid progress in recent years, with steady improvements in the number of qubits, the quality of qubit control, and the development of new quantum algorithms. As the technology continues to advance, the promise of quantum computers to revolutionize computing and unlock new scientific and technological breakthroughs has captured the imagination of researchers, policymakers, and the public alike. At its core, the power of quantum computers stems from the ability to leverage the fundamental principles of quantum mechanics, such as superposition and entanglement, to perform computations in a fundamentally different way than classical computers. By encoding information in qubits and exploiting quantum phenomena, quantum computers can, in theory, solve certain problems exponentially faster than the best classical algorithms. One of the most well-known examples of a quantum algorithm that can outperform classical algorithms is Shor's algorithm, which can efficiently factor large integers. This has significant implications for cryptography, as many of the encryption schemes used to secure online transactions and communications rely on the difficulty of factoring large numbers. A large-scale, fault-tolerant quantum computer running Shor's algorithm could potentially break these encryption schemes, posing a threat to the security of the Internet and digital communications. Another important quantum algorithm is Grover's algorithm, which can be used to search an unstructured database quadratically faster than the best classical algorithms. This has applications in areas like cryptanalysis, where quantum computers could potentially be used to break certain types of encryption by rapidly searching the space of possible keys. Beyond these specific algorithms, quantum computers have the potential to provide significant speedups for a wide range of problems, including optimization, simulation of quantum systems, and machine learning. The exponential growth in the size of the quantum state space as the number of qubits increases is a key factor that enables quantum computers to outperform classical computers on certain tasks. However, it's important to note that quantum computers are not a panacea that will solve all computational problems faster than classical computers. There are many problems for which classical computers are expected to remain more efficient, and there are also problems where quantum computers may only provide modest improvements in performance. The specific problems that can be solved more efficiently on quantum computers are still an active area of research. One of the major challenges in building practical quantum computers is the issue of decoherence, which refers to the uncontrolled interaction of qubits with their environment. This interaction can cause the fragile quantum state of the qubits to collapse, leading to errors in the computation. Overcoming decoherence is a critical challenge that must be addressed through the development of effective quantum error correction techniques. Quantum error correction involves encoding each logical qubit into a larger number of physical qubits, allowing the quantum computer to detect and correct errors. This is a complex and resource-intensive process, as the number of physical qubits required to reliably encode a single logical qubit can be quite large. Significant progress has been made in this area, but implementing effective error correction at scale remains an active area of research. As the development of quantum computers continues, it is likely that we will see a range of new applications and use cases emerge. Potential areas of impact include drug discovery, materials science, optimization problems, and machine learning, where quantum computers may be able to provide significant performance advantages over classical computing. However, it is important to temper expectations and recognize that the path to realizing the full potential of quantum computing is still long and uncertain. While the progress in the field has been impressive, there are still many technical hurdles that must be overcome before quantum computers can become a practical and widely used technology. One of the key challenges in assessing the potential impact of quantum computers is the difficulty in predicting the specific problems that they will be able to solve more efficiently than classical computers. The field of quantum algorithms is still relatively young, and researchers are continuously exploring new ways to leverage the unique properties of quantum systems to solve computational problems. As the development of quantum computers continues, it will be important to carefully evaluate the potential benefits and risks of the technology, and to ensure that it is developed and deployed in a responsible and ethical manner. This will require close collaboration between researchers, policymakers, and the broader public to address issues related to privacy, security, and the societal impact of this transformative technology. Despite the significant challenges, the potential of quantum computers to revolutionize computing and unlock new scientific and technological breakthroughs has captured the imagination of researchers, policymakers, and the public alike. As the field continues to evolve, it will be fascinating to see how quantum computers develop and the ways in which they may transform our world.
One of the key advantages of quantum computers is their ability to perform certain computations exponentially faster than classical computers. This is due to the unique properties of qubits, which can exist in a superposition of 0 and 1 states, and the phenomenon of quantum entanglement, which allows qubits to be correlated in ways that classical bits cannot. For example, Shor's algorithm, which can efficiently factor large integers, is a quantum algorithm that can break many of the encryption schemes used to secure online transactions and communications. This has significant implications for cybersecurity, as a large-scale, fault-tolerant quantum computer running Shor's algorithm could potentially compromise the security of the Internet. Another important quantum algorithm is Grover's algorithm, which can be used to search an unstructured database quadratically faster than the best classical algorithms. This has applications in areas like cryptanalysis, where quantum computers could potentially be used to break certain types of encryption by rapidly searching the space of possible keys. Beyond these specific algorithms, quantum computers have the potential to provide significant speedups for a wide range of problems, including optimization, simulation of quantum systems, and machine learning. The exponential growth in the size of the quantum state space as the number of qubits increases is a key factor that enables quantum computers to outperform classical computers on certain tasks. However, it's important to note that quantum computers are not a panacea that will solve all computational problems faster than classical computers. There are many problems for which classical computers are expected to remain more efficient, and there are also problems where quantum computers may only provide modest improvements in performance. The specific problems that can be solved more efficiently on quantum computers.
We're driving into the quantum internet. The quantum internet is a network of interconnected quantum computers that will someday send, compute, and receive information encoded in quantum states. Unlike the classical internet we use today, the quantum internet will not replace it, but rather provide new functionalities such as quantum cryptography and quantum cloud computing. While the full implications of the quantum internet are still unknown, several applications have already been theorized and some, like quantum key distribution, are already in use. Researchers estimate that interstate quantum networks will be established within the United States in the next 10 to 15 years, though a full-scale global quantum internet is still further off. Quantum computers use qubits instead of the classical bits used in today's computers. Qubits can exist in a quantum superposition of 0 and 1, allowing quantum computers to process information in a fundamentally different way than classical computers. This gives quantum computers the potential to solve certain types of problems, like factoring large numbers or complex logistics calculations, much faster than even the largest supercomputers. To unlock the full potential of quantum computers, they need to be able to process a large number of qubits. This is where the quantum internet comes in. By linking multiple quantum computers together, their computational power can be pooled, creating a far more capable system. However, transmitting and maintaining the delicate quantum states required for this is an immense technical challenge. One key application of the quantum internet is quantum cryptography, or quantum key distribution, QKD. QKD allows two parties to produce a shared random secret key known only to them, which can then be used to encrypt and decrypt messages. Thanks for your interest on emerging technology. Stay tuned by subscribing and clicking the notification bell on our channel for more amazing contents we're currently working on here.